And the first talk is accelerating NTT with RISC-V vector extension for fully homomorphic encryption. So let's welcome Alexander, give the talk.
Testing. All right. So thank you for the introduction. I'm Alexander, the second author, and I'm going to be presenting our work on accelerating NTT with RISC-V vector for FAG. So FAG doesn't need much of an introduction in our circles, but as you know, security in cloud computing is increasingly important, and there is some data that is subject to privacy regulations, such as medical records. And so the clients that use these servers must either trust the cloud providers, they must trust that the security is not going to be breached by a third party, or they can take matters into their own hands and use fully homomorphic encryption, which allows you to operate on the encrypted data, as you know. However, this has a really high computational cost, typically over 4 orders of magnitude, so it's pretty important that we accelerate these operations. At the core of FAG is the ring learning with errors problem, which requires polynomial multiplication, which if you have a polynomial of order p, that's going to be OP squared time complexity. And so as your polynomial grows, and it typically is pretty large in FAG, the time to do polynomial multiplication increases very fast. However, you can use the NTT, and this is going to reduce the complexity of the problem to p log p, because the multiplication itself is reduced to linear time. However, most NTT algorithms have pretty complex memory accesses, and so it's pretty challenging to vectorize them. Typically, when you try to use the compiler to do auto-vectorization, you can't really do it. It doesn't work. And most algorithms require scatter-gather memory accesses, which are a lot slower than traditional memory accesses. RISC-V, open source ISA. So the specification is completely open source. You can create RISC-V processors and sell them at no cost. You don't need to pay any royalties. I'd say what really makes them good is how modular, how flexible the fact they're modular makes them. You can pick from a variety of base sets, like embedded, and also application class, 64-bit, up to 128-bit. And then you can put a ton of extensions on top of that, a very important one being the vector extension. It's also undergoing really rapid adoption right now. There's funding initiatives from governments, from industry, and it's being adopted in a ton of contexts, from embedded to supercomputing, which I'd say is the most relevant one for FAG. Now, with RISC-V vector extension, you have 32 vector registers to play with. The vector length itself is microarchitectural, so each microarchitecture can define its own size of the vectors. It can get really large, up to 64K bits. And it's not necessarily tied to the processing width. So you can end up with 2 kinds of different architectures. So the top one is a short vector, and you can process the whole vector in one go. While the bottom example here is a really large vector, but you only process 8 elements at a time, so it takes multiple cycles. So at runtime, you configure the element size and type, and then you can write vector length agnostic code, which means the same code can run on architectures like the top one or the bottom one. It adapts at runtime. It has support for maxed operations, which is pretty important, and also for scatter-gather memory accesses, which we want to avoid, but it also helps. So right now there's 2 major versions in circulation. There was the trial version, essentially, which was released much earlier, 0.7.1, but some hardware ended up coming out for it before the ratified 1.0 version, and now we have those 2 kinds of hardware in circulation. Now, regarding NTT and INTT algorithms, there are plenty to choose from. The most common ones we see are Cooley-Tucky and Gentleman Sand. They're pretty simple, they're pretty fast, and for that reason they're used in libraries like OpenFAG. However, as we can see here, each stage has a different memory access pattern, and so this is quite challenging to vectorize, pretty difficult for a compiler to reason about. In our implementation of these algorithms, so we require some masking, which lowers the vector utilization and kind of kills the performance a little bit. So this is how Cooley-Tucky works, and Gentleman Sand is basically the same thing, just the other way around. Now Cornelambio and Pease, hope I'm pronouncing that right. The memory accesses, as you see, are constant, so the same every stage. This is pretty good for SIMD, so much simpler. However, the input and output indices differ, so we can't program it like we can Kulitaki and Gentleman Sands. We need a little auxiliary array and ping pong the values back and forth, which isn't ideal, but it's also not so bad for performance. Now, regarding our implementation of Korn-Lambiot and PEAS, we developed 3-stage algorithms for each. These do require an auxiliary array, but we don't need any masking, so we get full vector utilization throughout the entire process. The downside is that the routes of access do change per stage, but it varies with this variable m. We're going to see what m is exactly, but it still is a great advantage, despite this drawback. So regarding Korn-Lambiot, which we see up top, here we have an example for p equals 8 and vector length of 4. We can see that we can do regular loads, so each one of these represents a vector, and then we do the butterfly, and then one half of the butterfly is strided store here, and the other is strided store there. M starts at 1, and then it doubles every stage. PEAS is the exact opposite of what I just said, so instead we do strided loads, regular stores. M starts at p over 2, and at every stage it divides by 2. So here are the 3 different ways we access the roots of unity. These are the 3 stages of the algorithm. When m equals 1, which is the start of Korn-Lambiot and the end of PEAS, we only actually use one of the roots of unity. And so what we can do is vector broadcast. We basically just take this value, we splat it across the vector, and we can use it. When m grows, I'm talking from the point of view of Korn-Lambiot, PEAS is the other way around. But yeah, when m grows, we basically just have to load this, and then we have to use what's called a vector gather, which is we generate indices, which are going to pull from the original vector in order to distribute them like we see. It doesn't require any extra memory accesses. We just need to generate the indices, which isn't too bad for performance. Finally, when m equals the architecture's vector length, and here the vector length is in elements, it's not in bits, it starts getting too large for a single register, so we're going to need multiple registers. But we can use vector loads, so as you see, these axes are contiguous, which is nice. Now, it's not a big disadvantage that we need multiple registers because we make sure to reuse the roots of unity. So we only load them once. Basically, instead of going input, fetch the roots of unity we need, we fetch the roots of unity, and then we visit all of the parts of the input that needs these roots of unity. And we use it, depends on the stage at which we're in, the number of times we use them. Yeah, this requires a bit more complex indexing, but we still don't need any scatter-gather accesses, so performance is still great, still regular and strided accesses. There's also a special case, which is actually the one you see right here. As you see, we need 2 vectors, but not really because they hold the same values. And so in this case, we just do a single load. This, of course, is not true. As m keeps growing, we're going to need more and more vectors. We can't use this trick anymore. This is just for one singular stage. Now, to vectorize the modular reduction, this is pretty simple. As you know, the polynomial coefficients are between O and Q, Q being the modulus. And we want to avoid using the modulo operator. And so we know that when we perform multiplication, we can use the Shu production. And we also know that when we perform addition, we can use a simple modular reduction, which is just a subtraction. In order to vectorize this, we do masked operations. So essentially, we have the vector after an addition here. We compare it with Q, and this allows us to generate a mask. So this is going to have 1 in the lanes which the value exceeds the modulus. And then we just do a masked subtraction, which is just going to subtract Q. So here we splatted the value across the vector, but we're only actually going to do the subtraction in the elements we want. We integrate our codes in OpenFAG, which is an open source library. It's in active development right now, and it supports a ton of different schemes, which is nice. And this allows us to evaluate our code in a full application context, so we don't evaluate just the NTT speedups, we check the whole application. And it helps validate results. So we simply compile the library for RISC-V, we replace the NTT and INTT calls, link them with our implementation instead, and we can work with it. Regarding experimental platforms, we test 2 of them, RISC-V platforms. We have the first one, the vector processing unit. This is based on the Vitruvius Plus design. You can read the respective paper if you're curious about the microarchitecture, but it's basically a loosely coupled VPU. it looks like what we have up here. So it has the older standard, has a really large vector length of 16 kilobits, which works out to 256 64-bit elements. However, it only has 8 vector lengths, so it only processes 8 of those per cycle. In other words, it does 1 double operation per cycle. We use it prototyped on an FPGA, but it has in the past been tipped out on silicon you can touch. Not that you can't touch an FPGA, but you get what I mean. We also test the out-of-order processor, and in this case, the vector units are more tightly coupled with the core. So this is more like how AVX works, if you're familiar with Intel microarchitecture. It runs the newer RVV standard, and the vector length has to be a bit shorter because, in this case, it is tightly coupled to the vector length, our vector performance. So it would be a bit absurd to try a really big vector here. So we test between 1 and 2 vector units, and as I was saying, each of the units can operate on a whole vector per cycle. This is all simulated in GEM5, which is a computer microarchitecture simulator, and we try to match the whole architecture's parameters as closely as possible to a Qian Guo 6312U, which, as you're going to see, is going to be relevant. So here we're just comparing the speed up of the 2 different algorithms that we vectorized. So we have Korn-Lambio in blue and Kulittaki in gray. And this is equivalent, so Korn-Lambio is basically equivalent to Peas, and Kulittaki is equivalent to Gentleman's Sand in terms of performance. What we see is that Kulittaki seems to win out in the first few stages. However, as it starts to require masking, the effective vector utilization drops to half, and so it loses out a bunch of speed up compared to a scalar implementation. This is, in this case, is running on the VPU, which is on the FPGA. And so overall, Korn-Lambio and Peas seem to be significantly better than Kulittaki and NTT. I should add that Kulittaki and NTT are also what Intel Hexel uses, which is what we're comparing against here. So this is the state-of-the-art library for homomorphic encryption on x86-64. However, in order to get the most performance out of it, you need to have the AVX512 IFMA extension, which is only on a handful of server-class processors, one of them being the Qian Guo, which I mentioned previously. And here in this plot, we are comparing the peak performance of the 2 architectures. So the VPU, this is considering fused multiply-add instructions. The VPU can only do about a third of what the Qian Guo can do. However, when we compare the speed up of the NTT and INTT, we see that it's at least on par with Hexel, despite the fact that it has much lower performance. And as the value of P grows, here we test 3 different values of P, the VPU starts to win pretty comfortably. In fact, we see a bit of a trend here, which is as the value of P grows, the long vector architectures improve in performance and the short vector architectures decrease in performance. And this seems to be a property of the vector length of the architecture, not just the different algorithms and the different microarchitectures. Here we're testing the out-of-order core in GEM5. So again, we are averaging the NTT and INTT speedup. We test P equals 64K. And here we have a bunch of different vector unit configurations, 1 512-bit units, 2 units, a single unit with twice the size, and a single unit with, again, doubling that size. And we have the peak performance of each of the architectures. Once again, interestingly, despite the fact that we have significantly lower vector performance, we outperform the speedups of Hexel. We also see that vector length seems to have an influence on performance. So as you notice here, this is a shorter vector length. This is a larger one, but they are equivalent in terms of peak performance. And the one with the largest vector length seems to have quite a decent margin in terms of extra performance. We also see, interestingly, some diminishing returns as we increase the vector, as we increase the peak performance higher. And I believe what's happening here is that we are starting to become memory bound, and it doesn't make much sense to keep increasing peak performance in this architecture. Then we can take a look at speedups in the context of OpenFAG, whole applications. This is the simplest example we could come up with, which is just encrypting a ciphertext, performing a single operation, decrypting. In this case, we're using a P of 16K and running this on the VPU. This first example has no operation, it's just encrypt, decrypt. And yeah, we see speedups across the board for addition, subtraction, multiplication, rotation. And this applies to all of these schemes that we tested. We see higher speedups when we increase the number of bootstrapping calls. And one of the ways we can do this is by performing a multiplication chain. The more multiplications you do, as you see here on the x-axis, the more bootstrapping calls you're going to require. And that is going to increase the fraction of time spent doing NTT and INTT. And we can use Amdahl's law to calculate the maximum speedup that we could provide, assuming infinite acceleration of the NTT and INTT. And we see that our effective speedup follows the trend of the maximum speedup, which they both increase as the number of bootstrapping calls do. We also compare here the speedups, all again in OpenFAG, of 3-layer neural network. So this is a neural network that has 3 fully connected layers, and each layer has a ReLU activation. As you know, we can't do minimum and maximum operations in FAG. So what we do is we do a Chebyshev approximation to get the ReLU results. In the x-axis here, we're varying the network's layer size. And what we observe is that the speedup of our implementation running on the VPU seems to outpace the Hexel speedup by quite a decent margin. Interestingly, we also see that the speedup decreases as the neural network layer size increases. And we can explain this by the fact that the multiplicative depth stays the same. So we're only extending the dot product. And so the number of bootstrapping calls we're performing stays the same. However, as the network layer size grows, other operations increase in time occupancy. And so the benefit of accelerating the NTT and INTT decreases a little bit. So to conclude, we saw that our implementation of Kulitaki and Gentleman Sand. So given that the algorithms have varying memory access, and this leads to poor performance in some stages due to the fact that we require masking. I have some supplementary slides regarding these if you are curious regarding our implementation. On the other hand, Kornlambio and PEAS, they have constant memory accesses, which is much more efficient for us, and we can get full vector utilization throughout. Our speedups surpass Intel Hexel, which is the state-of-the-art library on x86, despite the fact that the architectures we test the RISC-V implementation in have significantly lower peak performance than the Xeon Gold processor we test Hexel in. We see significant speedups across full FAG applications, and in the future we wish to formalize the backend as an OpenFAG backend that you can pick when you're configuring it. And we also want to explore some further algorithms like higher radix, NTTs, and trying to fuse some of the stages of the algorithm. I'd like to thank you for listening. We have an artifact available, as you see here. And if you have any questions, I'll be happy to respond. Thank you.
Great, great. So we have 7 minutes for questions. Any questions?
Hello. So I'm the first in the line. So what's the degree of the approximation polynomial that you use for the ReLUs, I think? And how many, when you extended the network, you said that you didn't need to do more bootstrapping, but that would mean that you just extended the linear layers. Is that the case?
Right. So this is just is as you say. So we extend the linear layers. And regarding the degree of the polynomial here, I don't recall exactly. I'll have to get back to you. I can quickly check the paper. It's on the paper. But I believe it was 16K, if I recall correctly.
More questions? If not, I will ask a question. Not simple. But so if could you comment a bit on if you've kind of from a attacker's perspective, if someone wants to attack your implementation compared to previous version, that without this optimization, do you think it makes it harder? Or For instance, like you have this decryption in using NTT, and now you have this.
So I would say, so I'm not super familiar with side channel analysis and all those topics, but so I'm not sure if in that vein there would be much of a difference. But if we compare in terms of P, so as you know, if you increase the polynomial size, you also increase the security. And so what we see is, at least on long vector architectures, which RISC-V enables, and which aren't really common on existing hardware like x86, we see that this implementation tends to increase in performance as the polynomial size also increases. And so I believe this should help provide additional security guarantees, at least from attacks which are not looking at side channels.
Yeah, thanks. Thank you, speaker. Any more questions? If not, then we thank speakers again. So the second talk will be a high-performance NTT MSM accelerator for zero-knowledge proofs using load-balanced, fully pipelined Montgomery multiplier. Xianren will give the talk.
Thanks for the introduction. Hello, everyone. I'm Xianren Chen. It's my pleasure to have the opportunity to present our work. The title is a high-performance NTT MSM accelerator for zero-knowledge proof using Montgomery multiplier. This report is divided into 4 parts. First, I will introduce some background. Zero-knowledge proof is one of the most popular privacy-preserving protocols. It enables the prover to convince the verifier that a statement is true without revealing any private information. For example, Alice knows a solution to the Sudoku problem. She can use ZKP to generate a proof. Even though Bob cannot know the solution, she believes that Alice should know the solution. ZKP has 3 generic properties. The correctness and the soundness guarantee that 2 parties cannot cheat each other. And the zero-knowledge property ensures the privacy. So based on these properties, ZKP has a wide range of applications, including the cryptocurrency, blockchains, and outsourced computation for the machine learning, and so on. Among various types of ZKP, ZK-SNARK has another 2 important properties, say the succinct and non-interactive, which make it deployed on mature application system. The succinctness means small proof size and constant time verification independent of the application complexity. The non-interactive properties means one-time message passing from the prover to the verifier. The typical workflow of the ZK-SNARK consists of 3 parts. The trusted setup generates the prover key and the verifier key for the program. It can be multitasked by all runs of the same circuit. The proof generation is very time-consuming, especially for the large program. It consists of the iOS and the PCS. Their relationship is just like the bow and arrow. The main operations of IOP and PCS are the core-set entity and MSM, which are also the acceleration object. Finally, the verifier tests the proof. He only knows the public input, but cannot infer any private information. So in recent years, there are some very good accelerators for ZKP. However, many of the current approaches still use individual data passes for NTT and MSM, which will incur significant area cost. For the design of the Montgomery modular multiplier, the systolic array design or the digital serial design in previous works are scalable and have low area cost, but their architecture still involve feedback loops, resulting in low throughput compared to the fully pipeline design. So as mentioned before, the core bottlenecks of the proof generation are MSM and NTT. From personal view, the first challenge is the large-scale operations of different precisions. The vector size of NTT and MSM can be around 1 mega, and the operands can be hundreds of bits. The second challenge is the complex data flow and memory access. The costed entity will frequently read and write the off-chip memory, which will cause high access latency. The data flow of MSM is irregular, dynamic, and unpredictable, which requires efficient scheduling method. So if we focus on the proof generation process, one important observation is the serial data dependency between the IOP and PCS. So we can propose a unified and configurable architecture to accelerate the NTT and MSM without performance loss. To do this, we try to devise an efficient scheduling method, dedicated memory layout, and configurable modular multiplier. Finally, the aerial efficiency and the resource utilization can be greatly improved. Next, I will introduce our unified accelerator in detail. This diagram shows the overall architecture of our ZKP coprocessor, which is optimized from 3 main perspectives, including the memory access, arithmetic operation, and timing scheduling. In terms of the memory access, it includes the dedicated on-chip memory layout and DRAM layout. For the arithmetic operation, we design a configurable and fully pipelined P array to flexibly handle the NTT and MSM. For the timing scheduling, we propose the conflict-free and parallel scheduling for NTT and the load-aware arbitration for MSM. Next, I will go into some details of the design considerations for both NTT and MSM. For the large-scale NTT computation, at the algorithm level, we adopt a 2-dimensional NTT and INTT algorithm to partition the large-scale 1-dimensional vector into a 2-dimensional matrix. Take 16.2-dimensional entity as an example. This gives us 2 benefits. First, we can process independent small-scale entity for each row or column. Second, this method allows the on-chip memory to only accommodate several rows or columns, thereby elevating the pressure of memory usage. Moreover, for the sub-entity and sub-entity design, we consider 3 optimization points. First, we avoid the bit reversal issue by applying sub-entity and sub-entity with paired order. Second, we only use the JS type butterfly to reduce the butterfly cost by 1 less modular addition and subtraction. Third, based on the special properties, we also reuse the 12 factors of NTT for INTT to reduce memory overhead. At the hardware level considerations, we propose a conflict-free and parallel architecture where 4 rows are performed in parallel per batch, and each row computes 8 data points in parallel. We also design a conflict-free access mechanism for multiple memory banks based on a customized permutation network. So in this way, our multi-bank-based architecture can get almost full utilization compared to the previous SDF design. In terms of the timing scheduling, we use 2 DDR controllers and 2 memory sets to achieve parallel scheduling for on-chip computation and DRAM access. In this way, the batch processing period is the on-chip operation if the DRAM bandwidth is large enough. Finally, we get full utilization and reduce the overall latency. Okay, this figure gives the internal circuit structure of DDR4, which consists of 2 bank groups. And each bank group contains 4 banks. And each bank can be accessed by the row and column addresses. So if we simply store the matrix in DRAM row by row, it may incur large stretches when accessing the columns of the matrix, thereby leading to frequent row buffer miss and causing high access latency. To mitigate this issue and avoid matrix transposition, we adopt a block-based memory layout to store the matrix. First, we partition the logic matrix into blocks. Then, each block is mapped to each row of the DRAM. So accessing the data in blocks ensures that both row-wise and column-wise are performed with almost contiguous address. Next, I will introduce our design considerations for MSM. MSM is essentially an inner product operation. Pippinger algorithm is widely used to accelerate the MSM. It will change the order of summation and find the counters to reduce the number of point addition. So one trick is to represent the scanner in SAND format, which can have the number of packets. Each scanner is divided into H slices, which corresponds to the H times iterations. And each iteration consists of 3 phases, including the bucket accumulation, bucket reduction, and group aggregation. Since the phase 1 is most time-consuming bottleneck, with complex and dynamic data flow, which require an efficient scheduler to handle the colliding points and improve hardware utilization. As for the hardware considerations of J1 MSM, the overall detailed architecture is shown on the left, which includes the input memory, the dual port bucket, the point adder and MSM controller, and several state registers. We also propose a load-aware arbitration method to handle the dynamic data flow. For the sake of clarity, we use the simplified figure on the right to describe the arbitration method. We use 16-point MSM with 2-bit slice as an example. At the prologue phase, the output of point adder is invalid, so the result buffer is empty. If the output scanner is equal to the bucket index, the corresponding points are paired as inputs for the point adder. Otherwise, the new input points will be stored into the bucket. So in this phase, we can form 4 input pairs. And at the arbitration phase, the point adder has the valid result, so the result buffer is not empty. Based on the relationship among the result index, output scanner, and bucket index, the arbitration scenario is divided into 5 cases. For example, if the result index is equal to the output scanner, the point addition result and the new input point are paired as the input. Otherwise, the new input either goes to the bucket or goes to the point adder, while the result may be buffered or may go to the bucket or go to the point adder. So in this way, we can form 5 input pairs. At the epilogue phase, the result buffer is not empty, but the point memory becomes empty. So if the result index is equal to the bucket index, the corresponding points are paired as inputs for the point adder. Otherwise, the result is stored into the bucket. In this way, we can form 3 input pairs. So to sum up, the arbitration consists of these 3 phases and handles the dynamic data flow correctly and efficiently. Second, we further design a compact G1 point adder by spatial and temporal mapping of 12 configurable butterfly units. In this way, we can get the fully pipelined point adder and reduce the area cost. Next, I'm going to introduce the modular multiplier design. We identify the requirement for the design of modular multiplier for ZK-SNARK. The first observation is that the bit width of modulars for NTT and MSM under different curves is large and different. So the second observation is that the modular multiplier is intensively used by the high-level operations. For example, the unified point addition needs 12 modular multiplications, which are the key optimization point. We found that the typical fully pipelined modular multiplier is designed by directly unrolling and pipelining the fixed radix Montgomery algorithm. So the serial data dependency at the algorithm level will lead to unbalanced pipelined paths, which further leads to massive pipelined registers and low area efficiency. So to address these issues, we adopt 2 techniques. The first is the so-called quotient decoupling technique for breaking the data dependency and reducing the critical path. The core idea is to unroll the iteration and break the data dependency by changing the iteration order to form another periodical behavior. In this way, we can reduce the critical path since these 2 multiplications can be performed in parallel. The second technique is the multi-radix representation, which are inspired from the square root carry adder. It uses the multi-radix form to balance the carry path. So we can gradually increase the bit width of the blocked operands with the reduction stage, so that the accumulated pipeline registers can be fully used to pipeline the sub-multiplication, leading to a more balanced pipeline partition. So this figure shows the instantiation of the fully pipelined load-balanced Montgomery multiplier for BLS curve with 2 bit widths. In addition to the previously mentioned quotient decoupling and multi-radix representation, several other optimization techniques are also employed. By integrating all these techniques, we can improve the area efficiency of the modular multiplier. Now, I will go to the final section. We compare the proposed new algorithm with other algorithms in terms of theoretical complexity. The algorithm can support 2 bit widths of modulars and have shorter critical paths within 1 iteration, and have reduced the number of multiplication and iteration. We also synthesize the modular multiplier designs to evaluate the optimization objects. The experimental results show that the load balance technique can reduce pipeline registers and improve area efficiency. We evaluate the overall architecture for the functionality comparison. Our accelerator supports both entity and entity, entity and MSM with a unified method, which leads to 4 times less area cost compared to PyZK. For the entity and MSM comparisons, our work also achieves notable speed ups, which also maintaining high real efficiency. So we conclude the report. We propose a unified and efficient accelerator for both entity and MSM. Employ comprehensive optimizations, including the memory partition, the timing scheduling design, and the arithmetic unit design. Thanks for your attention. Questions are welcome.
So, any questions? So maybe I ask a question. I'm a bit not in this. So is this a constant time?
Thanks for your question. Yeah, the related operation is constant time, and it can resist to simple timing attack. But for the power-related attacks, we cannot consider at this time because our design is mainly applied in the server side. So the side channel attack may not be a priority thing. Yeah.
Let's thank the speaker.
Okay.
Yeah. Let's thank the speaker again. Thank you. So the third talk is faster amortized bootstrapping using the incomplete NTT for free. Taylor will give the talk.
Okay, thanks everyone for attending the talk. Okay, so there are two main approaches for FHE bootstrapping. The first one is for BGV and BFV-like schemes. The other for FEW and TFHE. So for BGV and BGF, the latency or the time for bootstrapping is very slow, but the amortized time when you apply one bootstrapping operation for multiple ciphertexts at one time, it's very fast. But for FEW TFHE, it's the opposite. The latency is very fast, but the amortized time is very slow. So this is what we are trying to improve here. So our contributions is that we improved the amortized bootstrapping algorithm for FEW TFHE style schemes. We use the incomplete NTT, or we show how to use the incomplete NTT for free to improve performance of state-of-the-art. So if you know the NTT, you know that typically the base move starts getting on the way when you try to use more incompleteness levels. But we show that this is not the case for these types of schemes because you have to use, you're bound to use a very small multiplication depth for your operations. And then we do a parameter selection that explores different trade-offs for choice of modulo and performance and the FRs, or the decryption failure rate and reliability of the scheme. So, okay, so for LWA ciphertexts, to get LWA ciphertext, what you do for encrypting a message M, you sample a vector A and a small element U of ZQ. Then you compute B equals to the dot product between A and Z plus E plus delta M, where delta is the scaling factor that will help you get to the right or decrypt to the right message afterwards. And then you get this pair, which will be your ciphertext. And decryption is simply you sum B to the dot product between A and Z. But for the bootstrapping corresponds to the homomorphic evaluation of the decryption circuit. So you're given encryptions of each element or each integer that is part of your key, and then you apply the same operation, but now Z, you have encryptions of the elements of Z, right? So you have to do some scalar multiplications homomorphically, and then you hopefully get your an encrypted version of your message, and hopefully with a smaller noise than you started with. So the problem with this is that the complexity when you use n messages, it's n squared, right? So for bootstrapping n messages, the complexity is n squared, which can be very inefficient for real-world schemes. So To deal with this, Michencho and Sorel presented an amortized bootstrapping technique where you pack n ciphertext into an RWE ciphertext or a ring LWE ciphertext, and then you perform n bootstrappings at once using one ring or one polynomial multiplication. So this is done in 3 steps. So you start by packing your bunch of LWE ciphertext into one ring LWE ciphertext that now you get 2 polynomials, A and B. So these are not vectors anymore, these are polynomials. And you homomorphically compute A times Z, where Z is an encryption of your secret key plus B, right? And then what you do is you do an homomorphic rounding or an extraction of the most significant bits to get the right coefficients of your polynomials. So there are some implementation challenges on these types of, on the amortized bootstrapping for field presented by Michencho and Sorel. And the main bottleneck is that it uses these RGSW registers that only support homomorphic addition. So while in theory, to bootstrap n messages with this cost here, it will give you this amortized cost because you're dividing it by n, so you get rid of this exponent here. In practice, it gets even worse than sequential fill because of the very high overhead when you're doing the scalar multiplications. So the key observation from Guimarães et al. And also by De Micheli et al. Is that we can efficiently perform homomorphic scalar multiplication in RGSW register, and hence we can use the NTT for applying the homomorphic INTT that allows you to get some speed up when doing the amortized bootstrapping. And this gives you a better asymptotic complexity and small overhead. So to use the entity for fast multiplication of these polynomials here while doing the amortized bootstrapping, so notice that you're working with prime p and n is a power of 2, so you are in an entity-friendly setup if you're smart when choosing p and n. And the main goal is to compute like the most expensive part, which is the product between A and Z. And to do that homomorphically using the entity, you're given an encryption, actually an encryption of the entity of Z, and you start with A, which is part of your ciphertext, compute the entity of A, then you do the base multiplication between the elements in the entity domain, which would require some scalar multiplications in the encryption domain. Then you apply the inverse entity to the result, and you get an encryption of your message, or sorry, an encryption of A times Z. Then how to homomorphically compute the inverse entity? So typically the entity is defined as an iterative algorithm. That's what we use for Kyber, what we use for dilithium, and where the goal is to have it as fast as you can. And to do that, you do this bunch of FFT-like style algorithm that gives you n log n complexity. But then the layers, so the elements from the last layers are combined using these butterfly operations. But the problem is that each layer will increase the depth of multiplication because you have to keep multiplying it by the pseudo factors in each level. So the error can grow too much. So what Guimarães et al. Do is that they fix the multiplication depth on 2, and then they compute the inverse entity using a radix M approach, where you divide your entity computation into, or the inverse entity computation into 2 blocks. They are more expensive than the iterative entity that we know, but they allow you to compute the inverse entity without the error growing too much. So, but the limitation of that is that the radix M formulation requires the complete entity for you to get an analytical evaluation of how to apply it. So in particular, it needs a 2n root of unity in ZP, and this limits the use of more efficient parameters that you could get for n and for p, right? So the solution, because we want to get this flexibility on choosing the core parameters, what we do is we try to apply the incomplete entity to this scheme, to this construction, and actually to the implementation by Guimarães et al. So this will give you more flexible parameters that might improve performance or reliability in the form of decryption failure rate. But the problem is that it's tricky to define the incomplete radix M entity and the corresponding base multiplication algorithm. So okay, so our approach, first we start by trying to define an incomplete entity in the in the radix M approach. And then we show the problems that we have for the base move and how we solve that. So to get an incomplete two-part entity, what we do is we get a fixed prime, a power of 2n, and an incompleteness level that we want to achieve, L. So for the complete entity is when L is equal to 0. Then we remember, of course, that the identity, such as just like the FFT and the inverse FFT, it's a linear operation. So we have a matrix that is associated with the inverse entity. And these M factors into products of butterfly matrices, just that corresponds exactly to the circuit that I showed you before. So, so we get a product of log 2 of n minus L, the incompleteness level that you want to achieve, matrices. And here are the example. They are very structured, and they correspond directly to the circuits that I showed before. And then to define a two-part entity, you simply choose a breaking point alpha to factor M as a product of two matrices. And then you construct MB and MA, like these two matrices that are both structured and somewhat sparse, depending on how you choose them. But the multiplication by MA then by MB has the same complexity as the two-part radix M done by Guimarães et al., which is nothing new here, right? We're just splitting the inverse entity into linear, putting it into a linear algebra setup. Now the thing is, when you do the incomplete entity, you have to be very careful to not usually not use too many incompleteness, because you end up having to multiply polynomials whose degree grows exponentially with the incompleteness level that you're trying to achieve. So the problem is, so the base multiplication, which is the multiplication of polynomials in the entity domain, can make our approach, or this incomplete entity in radix M approach, less efficient than simply the two-part entity that is used by Guimarães and others. So, but the good news is that the base move, of course, it's also linear. So we have a matrix representing the base move, and we can build a block matrix A hat with all the base moves required. And the thing is, now what we have, it's also very simple, like nothing really new here. We have a simple representation of the inverse entity and the base move as in a linear algebra setup. But what's the reason why we will be able to see some speed up? It's because of this observation here. So this product between MA and the base move matrix is a product of two diagonal matrices that are very structured. And the thing is, if you say that X is equal to this product here, when you do this actual product between these two matrices, you get this shape here. And this shape ends up being exactly the shape of the first part of the two-part inverse entity used by Guimarães and others. So you don't get any increase in complexity when you multiply by X. So we call that the embedding of the base move into the matrix X. So this allows us to get what we call an incompleteness for free property of that. So we have the alpha star is the best parameter alpha for separating the multiplication by the inverse entity into two parts. And this you call alpha star to be the best balancing factor you can get for using the original implementation. And then the incompleteness for free property is that when your level of incompleteness is less than or equal to this number, to the log 2 of n, and this best splitting parameter, then the operation count for doing their original two-part split or two-part inverse entity and ours inverse entity, incomplete inverse entity with the embedding of the base move is exactly the same. So why is it useful to us? Because for you to get faster bootstrapping in this setup, the performance depends on the bit length of B. But if you want more reliable bootstrapping, the failure rate will decrease with larger P. So you have this. You have to deal with this balance, right? So because of this, because the faster bootstrapping depends, or the time of the bootstrapping depends mostly on the bit length of P, not in its actual value. So we effectively we want P to be closer to, but below powers of 2. Because when the bit length increases, then the performance or the time for bootstrapping doubles. So we want to get as close as possible to these powers of 2 here, right? And the problem with, or the limit of the the original implementation, is that you are bound, if you want to use for these parameters, like n equals to 1024, and p, and p of 14 bits, with the complete entity, you are bound to use only this value, right? But with the incomplete entity for free, we can use this value here with almost the same complexity, but with a much better DFR. And the thing gets even better for our case when we consider that with 15 bits primes, you are bound to use this value, which is very, very far from this one. So this flexibility allows us to get a much better results both in performance and in reliability. So for these cases, we're considering n equals to 1024 and to 2048, for which we were able to compute that doing the alpha stars computation, that we get L equals to 4 levels of incompleteness for free. So using that, so the original implementation achieves this value for the amortized time and 2 to the minus 17 DFR. And our case, with the more flexible primes, we're able, for example, to double the speed up with a cost, well, like with an increase in the DFR. But we have strictly better parameters, actually. We can drop the DFR by a lot and also have a 40% speed up. We are also able to achieve 2 to the minus, less than 2 to the minus 128 for 8-bit messages, which is not something that seems to be possible for the original implementation. So we also consider to benchmark with the state of the art with the sequential implementation, right? Because sometimes these amortized algorithms are not yet faster than the sequential ones for the same family of schemes. But comparing to TFHE RS, which is the state of the art for sequential bootstrapping, we actually were able to be faster than them, but the DFR is much, much higher, at least for 8-bit masters. So there is this caveat. But of course, this is the same for Guimarães and others implementation. Okay, so the key takeaways is that the incomplete NTT can be strictly better in some FHE cases. So keep in mind that when your multiplication depth is small, maybe you can possibly try to apply these tricks. So we were able to improve the state of the art for practical amortized bootstrapping. So by using this concept of NTT completeness for free, that gives us more flexible parameters, which gave this a significant impact both on reliability and speed up. So there are some concrete explorations for different cases, like for optimizing for performance or reliability. When you're, like, for example, trying to, if you have very small bit messages, then you can optimize for performance because the DFR, you'll be able to lower the DFR together with increased performance. There is this particular case of being faster than TFHE at the cost of a much higher DFR. And this confirms some theoretical possibilities raised by this previous work of ours, like where we evaluate some possibilities of using the incomplete entity in FHE. And for future work, the main question is how to lower the DFR to make it possibly faster than TFHE with an acceptable DFR. So we possibly have to explore some different parameters that we cannot explore here because it takes a lot of time to try to optimize these FHE parameters. But maybe with more time, we can possibly find some better parameters. So that's all for me. Thanks for attending this.
So any questions? Yes.
Thanks for the talk and the paper. So I have both a question and a suggestion, but I will ask the question first because maybe the suggestion is invalid because I don't understand it enough. So it seems that the incomplete NTT is necessary to get your nice P, and the nice P is what drives your performance? Or is it the case that having the incomplete NTT itself without picking a nice P would also give you better performance?
Thanks for the question. It's exactly what you said first. It's the fact that you use a different P that you get better performance. The incomplete entity we run in exactly the same time. If you use the same P.
Okay. Then my suggestion kind of becomes invalid, but I was wondering, would it help to use the four-step NTT in some way? Because right now, when you were talking about the problem being that like doing an NTT requires going for log n layers, you could do the four-step NTT, or it's also called the two-dimensional matrix, like split it up into two parts, then you only get 2 layers, for example, or you could split it up into 3 parts or whatever. Like if you're doing 1024, you could do 2 to the 5, 2 to the 5, then you only have 2 layers. You do have to deal with like a 2 to the 5, 32 coefficient wide.
But if I understand that correctly, this is kind of what Guimarães and others do, because they are using the complete entity. But that setup, you don't have the incomplete entity, right?
That's true, but I guess that I thought that Guimarães et al. Actually combined. Like they don't do that 2 to the 5 naively. They actually like use butterfly circuits, which are radix 2, rather than say just running a polynomial.
Oh no, they actually run it's kind of the same of the matrix split. When you implement that efficiently, you compute every index and you do the multiplication. They do some embedding also of the base move, but the base move is trivially like just a multiplication, like a pointwise multiplication, because they're in the complete entity domain. So, yeah, I think these ideas can be applied, but you have to do the embedding of the base move if you want to see some speed up, right? Together with the incompleteness.
Okay,
Yeah?
thanks.
Thanks, John.
More questions? So tell us how, so you mainly compare with TFGI, or how about the performance compared to other?
Sorry, Ken?
How about the performance compared to other libraries?
Okay, to
Did
other
you try
libraries,
some?
I expect it to be much worse, but we're trying to compare with the same family, and what we have is, I think the state of the art would be the TFHE RS, which is sequential, and it's weird to try to beat the sequential with like a more complex setup, but yeah, I think the only like honest comparison we can make is that with the state of the art, which is TFHE RS. Thanks for the question, Joe.
If no questions, then we thank the speaker again. This concludes the session.